Hi everyone, my name is Jun. I am glad to be here to present today. The original slide has about 85 pages. That's only 12 minutes to present, and it's too short to give comprehensive information in this presentation. I will skip some pages. The architecture of Rabbit can be divided into front-end and back-end. The front-end translates the guest binary or source binary into LLVM-IR blocks. The backend translates the LLVM-IR blocks to the host binary. Binary translation can be classified into three classes. Static binary translation translates code blocks in compilation time. Dynamic binary translation translates code blocks in runtime, and hybrid binary translation is comprised of SBT and DBT. In the translation phase, instructions of guest binary are translated into many code blocks, which we call translate code blocks, or TCB. Take an example. The successor of block 1 is block 2, whose address is 12000. The TCB of block 1 gets the value of A5 register in the end, and the TCB1 needs to know where it should go. TCB1 needs to pass the source address, which we call source program counter, or SPC, to the runtime dispatcher to find out the address of the successor block in host machine, which we call the target program counter, or TPC. And the runtime dispatcher looks up the address matching table, finds out the destination, and transfer control to the TCP2, which is translated from block 2 in guest binary. Every source block ends with the instruction Terminator, which can be classified into two groups, direct branches and indirect branches. Direct branches has single destination, and it is possible to know the destination in compilation time. For example, a branch with equal instruction whose joint target can be calculated by PC relative addressing. It gives us a chance to optimize the block with direct branch without going through the runtime dispatcher. Indirect branch may have single or more than one destination. The destination may be stored in a register or a memory address. It's difficult to predict the destination without context information. Because there are some restrictions for block training optimization, we developed Hyperchaining, an improved version of block training optimization, which be able to handle indirect branches and decide to work well with HBT and Rabbit. Depending on the implementation, hyperchaining optimization can be classified into two groups. One is platform-independent hyperchaining, and the other one is platform-dependent hyperchaining. For platform-independent hyperchaining for direct branches, we design a subroutine, direct branch training handler, to chain blocks for direct branches. Basically, platform-independent hyperchaining optimization is implemented in LLVM-IR level, so we don't need to take care about the underlying architecture. The direct branch training handler will not only chain blocks, but also support some functionality runtime dispatcher provides, like DBT and address lookup. Every translated code block with direct branches is given a dedicated memory called TransferDestination, and the TCB loads the address from its TransferDestination memory. In initial state, the TransferDestination is initialized with the address of intermediary, which calls the branch training handler to train blocks. Update TransferDestination memory with TPC and transfer control to the next translated code block. For platform-independent hyperchaining for indirect branches, we have another subroutine, indirect branch training handler, to handle indirect branches. This one is also implemented in LLVM-IR level. Because indirect branches have one or more destinations, in platform-independent hyperchaining for indirect branches, we have a joint destination cache to store every visiting destination. We observe some phenomena in platform-independent hyperchaining. For direct branches, TCP need to read the same TCP of successor block every time it executes. It can be perceived as a redundant operation. For indirect branches, it's possible there is only single destination, but we leave a jump destination cache, which takes many memory space for such cache, and is an efficient way. So we design platform-dependent hyperchaining to deal with. In our design, the platform-dependent hyperchaining is based on the platform-independent hyperchaining. If platform-dependent hyperchaining fails, we can use platform-independent approach to deal with. Here's the idea. Maybe we can simplify the redundant operation, which reads the TPC of the next block from its transfer destination. Maybe we can direct patch destination into the code, which is at the last part of the translate code block, which read the transfer destination. Before patching the code, we need to set an anchor point in the instructions memory of translate code block to tell where chaining handler start to analyze the code. In x86-64 architecture, no if active address instruction permits the program counter as its source operand. We minus an offset to the program counter to get the address of the wrong effect address instruction itself. And we store the anchor point into a certain entry of the CPU context. There we load the address of transfer destination and map the reference. And recover the calling set register of the first parameter and jump to the successor block. This instruction constitutes code pattern 1 in our definition. Then, how to patch the destination into the instruction. The usual way is patching the last instruction. And unfortunately, it's impractical because there are some issues. Patch out the boundary problem and conditional branch block problem. For such concerns, we don't patch last instruction. We pick move absolute address instruction as the proper one because this instruction offers enough space to patch. We copy move RDRACX instruction to the front to recover calling set register and patch the jump instruction to the success block. If the displacement is too large to be encoded as a direct jump patch, we use Indirect-Branch Patch. The patch code is just like this one, and we disable the dereference. In code pattern 2, you will notice there are less instructions in comparison with the code pattern 1. Now RDI holds the CPU context. In code pattern 2, we can directly patch destination in the front. Next, we go forward to the part of platform-dependent hyperchaining for indirect branches. In our study, there are about 73% of their branches which are not function return, but have only a single jump destination. We need to take care of single destination case. Here we adopt code cap to deal with single destination indirect branch. Code cap is one or several consecutive instructions in which some fields are intentionally filled with dummy values in the beginning, and these fields are patched with data related to the branch such as SPC, TPC, etc. It is a code cap. In initial state, these two instructions can be viewed as node instructions. The last two instructions take 14 bytes and are reserved for a direct jump patch or a indirect jump patch. In indirect branch chaining handler, the handler does address lookup and patches SPC, TPC, register, and a direct jump into the code cap. A direct jump patch takes 6 bytes here and there are 8 bytes left. We patch a node instruction here which takes 8 bytes. Or patch an indirect jump here. If the lookup fails in the code cap, It means the indirect branch has more than one destinations. The code cap is disabled by patching a jump instruction, and the jump instruction will transfer control to a block of memory, which contains many SPC and TPC pairs, and looks at the destination. The block of memory is called dynamic address matching table. If the lookup fails in the dynamic address matching table, the control is transferred to the code of calling indirect branch chaining handler block and bypass the cookie path. Here is the structure of dynamic address matching table. We divide the memory block into two separate sections. The first section contains only SPC and the other one contains only TPC. If that's the SPC entry in the first section, there must be a corresponding TPC entry in the second section. If the lookup fails, the control is transferred to the cookie. If there are more SPC-TPC pair is coming, the original jump cookie instruction is overwritten, and a few instruction is patched, and a new SPC entry is created. So does the second session with the new TPC entry. This paper proposes platform-independent hyperchaining and platform-dependent hyperchaining on the x86-64 platform. The experimental results show platform-dependent hyperchaining can reach 1.08 times and 1.05 times speed up compared to platform-independent hyperchaining.